This week we'll be focusing on recursion, which is covered in chapter 18. So recursion is an approach to solving a problem. It involves breaking a problem up into smaller problems that are easier to solve than the original problem. And the idea is that you just keep breaking the problem up into smaller and smaller problems until the problem gets so small that it's really easy to solve. And then oftentimes you use that final solution to kind of build back up the solution to the original problem that was much bigger. Another way to say that is if the problem is easy, I'm just going to solve it and be done with it. But if the problem is hard, I'm going to solve a small piece of it, so break off a little chunk that I can do now. That leaves the problem smaller, and I'll solve the rest of that smaller problem later on. So when we use recursion in programs, we write what's called recursive methods. So the different elements of our recursive methods are an execution of a small part of the problem, so that's breaking off a little chunk of the problem, solving it now, and then calling that method, so calling the same method that we're currently in with the reduced problem. So I basically say, okay, I'm going to solve a little bit now in the current method, and then I'm going to call the same method again, only with a smaller version of the problem, and solve that. That's essentially our way of solving that part of the problem later. So what we have to have in our recursive methods is a base case or an escape clause. We need to know there needs to be some way where we indicate that the problem is small enough that we can solve it now, and that basically we're done solving the big overall problem. So that base case is the non-recursive part of the method. Without that base case, there'd be no way to know when we're done. We would just keep calling the same method, making the problem smaller and smaller and smaller until infinity, which is bad. So we need that base case. That tells us when the problem is done, when the recursion should stop. So let's take a look at just generally the idea of recursion, and the kind of classic recursive problem is factorial. So factorial is a concept from mathematics that hopefully many of you are familiar with. It's indicated with n exclamation point to indicate the factorial of n. And n factorial is defined as the product of all integers between 1 and n. So 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, and so on. So this is what a factorial is. Now we can define factorial by using recursion, because you can note that for any number n factorial is equal to the number n times the factorial for n minus 1. So this is essentially saying, okay, n factorial is a hard problem. I don't know how to solve it. But if I knew the answer to a smaller problem, if I knew what the factorial was for n minus 1, so n minus 1 is the smaller problem, then all I'd have to do is take this little part that I can do now, multiplying by n, and I'd have to take that and multiply it by the solution to the smaller problem, and that whole thing would be the solution to my bigger problem. So again, the idea is solve a small part now, multiplied by n, and then solve the same problem but on a smaller input, n minus 1 factorial. That's the recursive definition. The other part of that is specifying a base case. So my base case is, well, let me figure out what the answer is to a really, really small and easy problem, and for factorial, that's just 1 factorial. If I want to solve 1 factorial, it's just 1. So the idea is, again, solve a small part of the problem now, then make the problem smaller and solve it later. Okay? So if we, for example, wanted to find the factorial of 5, we could say, well, that's a big, hard problem. I don't know what that is. But if you told me what the answer to 4 factorial was, all I'd have to do is multiply by 5, and then I'd have my answer. So this is the solve now part. This is the solve later part. Okay, so then solving later, 4 factorial. Well, I don't know what that is, but if you could tell me the solution to a smaller part of the problem, 3 factorial, all I'd have to do is multiply by 4, and I'd get the answer. Okay, I don't know the answer to 3 factorial, but if you told me a smaller part of the problem, 2 factorial, I'd have to multiply by 3, and then that'd give me the answer. Well, I don't know the answer to 2 factorial, but if you could tell me what the answer to 1 factorial is, all I'd have to do is multiply by 2, and that would solve that part of the problem. Well, I actually do know the answer to 1 factorial. That's my small problem that's easy to solve. It's just 1. So now I can use the answer to this small part of the problem to build back up. So I know 1 factorial is 1. So since I know the answer to this small problem, I now know the answer to 2 factorial. It's 2. And since I know the answer to this small part of the problem, I can find my answer to 3 factorial. It's 6. and I can send that back up a level. And since I know the answer to this smaller problem, I can now solve 4 factorial. It's 24. And since I know the answer to this smaller problem, I know the answer to 5 factorial. It's 120. So again, you can see here the idea is that we break off a small piece of the problem and we then solve it now. And we oftentimes combine that solve now part of the problem with the solution to the reduced problem. So again, when we're doing this kind of programming, we write recursive methods. Now, recursive methods can be void, meaning they do something but don't return a value, or they can return a value, and we'll look at examples of both. But the bottom line of what our methods have to include is a base case, so they have to include some way that our recursion is going to stop. And then they include the recursive case, so that's the case where the method calls itself again with a reduced problem. And that means that somewhere in there has to be a conditional, because we have to determine, okay, if we're inside this method, are we in the base case, meaning that the recursion is done, or are we in the recursive case, meaning that we should invoke the current method? So all of your recursive methods should have these 3 pieces: the base case, the recursive case, and a conditional to figure out where you are. And your recursive case should always make the problem smaller. Now, the key thing to understand about when we write recursive methods is that every call to that method sets up a new what's called execution environment. So every time you call any method in Java, there's a little activation record or execution environment. You'll hear both terms used. And that record contains information like the value of the actual parameters and any local variables that are declared inside that method. So that happens when you call any method, and that also happens when you call recursive methods. Now, this is where it gets a little bit more confusing with recursive methods because they actually have the same name as each other, right? If we call the same method 5 times, that method's going to have the same name. But each time that method's called, it gets its own activation record or its own execution environment. And that's really, really important. So we're going to look at an example of what that means. So let's look at a quick example of what that means using this problem here, summing up of integers. So this is similar to the factorial problem, only we are summing up integers instead of multiplying integers. And the problem we're going to solve is summing up all the numbers between 1 and some integer n. So we can see that we can define this recursively because the solution to that problem is really hard. I don't know it, but I know if you could tell me the solution to n minus 1, all I'd have to do is add on n, and that would be the solution to the whole problem. And then we can further say, okay, well, how do I solve the problem for n minus 1? Well, I don't know, but if I could solve it for n minus 2, all I'd have to do is add on n minus 1, and then I'd be done. Well, I don't know the answer for n minus 2, but if I could solve it for n minus 3, then all I'd have to do is add on n minus 2, and I'd be done. So that's our recursive definition. What is the base case for this little problem here? The base case is going to be, again, when n is 1, because if we want to sum up all the numbers between 1 and some positive integer, if that positive integer is 1, the sum is just 1. So the base case is 1. Okay, so before we look at the solution to this problem, we're going to quickly look at the example about activation records and the runtime stack on just a non-recursive problem, and then we will solve this practice problem using recursion and look at what that means for the activation records. Okay, so this is our little non-recursive example here. What I do is I have 3 methods, method A, method B, and method C, and they have 2 parameters each, an integer and a string. And you'll see that these methods really don't do anything exciting. So method A, all it does is it prints out the parameters, and then it subtracts 1 from x, and it cuts off the last letter of the string. Okay, so it just truncates the string by 1, and then invokes method B with that new number and that new string. Method B does the same thing. It just prints out the parameters, subtracts 1 from x, cuts off 1 character from the string, and then invokes method C, and method C just prints out the parameters. Now in my main method, I initially declare x to be 2, my string to be hello, and then I'm going to invoke method A with those parameters. So when I run this program, nothing all that exciting happens. We just print out that in method A, x is 2 and s is hello. In method B, x is 1 and s is hell. And in method C, x is 0 and s is hell with 1L. Okay, so this is not a very exciting program, but you can see here we just have three methods, method A, B, and C, and again, each of them has some formal parameters. Each of them also has some local variables, right? So this is a formal parameter of method A, X, and S is also a formal parameter of method A. Y is a local variable to method A because it's declared inside the method. That means that while method A is running, Y is saved in memory, and when method A is over, Y is garbage collected. Same thing for S1. This is a local variable. So let's take a look at what this means in terms of activation record. So here's how I'm going to display that. Every time we invoke a method in Java, we get an activation record, and that activation record specifies what the method is, the formal parameters, and the actual parameters that are sent in as values. So this is actually both the formal and the actual parameters, and the local variables. Okay? Now, when the method gets invoked, all of this information, this little activation record, gets placed on the runtime stack, on the bottom of the stack. And that means that's whatever method is on the top of the stack is the method that's currently running. When that method completes, that activation record is popped off the stack, and whatever method was below it resumes with control and starts running. Okay? So let's see what happens here. So our first method that we invoke whenever we run a program is main. So our method is main. Our actual parameters are our string array args. Don't have any value for that really because I didn't put any in any arguments. And our local variables, as we go through this method and execute it, we declare an X and we declare an S. So that's our currently running method because it's in the top of the runtime stack. And then we invoke method A. So what happens is an activation record gets created for method A. So my method is method A. My formal parameters are X and S. And the actual values sent in are the ones that are sent in when the method's invoked, which is 2 and hello. And this method now gets put on the top of the runtime stack, like that. That means the main method is kind of paused, waiting while method A is running. So method A executes, we have our print line, and then we declare some local variables, Y and S1. And then we invoke method B. So we get an activation record for method B. Method B has some formal parameters, X, which is sent in the value of 1, and Y, which is sent in the string of HELL. And then inside method B, there's also some local variables declared, Y and S1. So because method B is currently running, it gets placed on the top of the runtime stack. So method B executes, it does a print line, declares a local variables, and then it invokes method C. So method C now gets an activation record. And it also has some formal parameters, X, which is sent the value of 0, and S, which is sent the value of HEL. It doesn't actually declare any local variables. It gets placed on top of the runtime stack. Okay? So when method C, what you can see here is this is the current runtime stack if we're down to this line in the code as we're executing, the print line inside method C. And when method C now executes, when it finishes executing, what's going to happen is we're going to pop this method off the runtime stack. But let's just take a look at the stack right now. What we have is we have an activation record for every method that's been invoked. So main invoked method A invoked method B invoked method C. And for each one of these methods, we have information about the formal and actual parameters for that are local to that method, and the local variables that are also local to that method. So these formal parameters that are given the values of actual parameters and these local variables are visible only inside this method. So these X and S, this X and this S are only visible inside of main. Args is only visible inside of main. This X and this S are only visible inside of method A, and this Y and this S1 are only visible inside of method A. So each method gets its own activation record, and those formal parameters and those local variables are visible only inside that activation record. And these activation records don't talk to each other. So this method can't borrow anything from this method unless it's sent in as a parameter. That's the only way to pass information in between methods is through a parameter. Okay, so when method C finishes executing, what happens is we pop it off the stack and it's done. And then method B will finish executing because it's at the top. And then when method B is done, we pop it off the stack. Oops. And it's done. And then method A is on the top of the stack, so it'll finish executing. And when it's done, we pop it off the stack. It's done. And then main will finish executing. And when main is done and we pop it off the stack, there's nothing left on the runtime stack. And so our program is done. Okay, so that's how it works with just all of our normal methods that we call. It works exactly the same way with recursion. The only difference is instead of popping on method A, method B, method C, pushing on and popping off method A, method B, and method C, we're going to be pushing on different activation records from the same method. But that method gets treated just like any other method. It just happens to have the same name as the method that invoked it. So let's take a look at how we would write this method here for summing up integers. So we'll do this from our same program. So we're going to write a recursive method, sum integers, and we'll take in one parameter, the number that we're going to sum up till. So this will be like n. And we need two things. We need a base case and we need a recursive case. So our base case is when we know our problem is done. So when we know our problem is small enough to solve right away. So we said that our base case is going to be 1. So if our number is equal to 1, that means we're in our base case. And we said the solution to our problem when the number is 1 is just 1. So here, if we're in the base case, we'll just return 1. Because the sum of all integers from 1 up till 1 is just 1. So if we're not in our base case, we're in our recursive case. So for our recursive case, what we want to do is we want to solve the little bit of the problem that we can solve now, which if we look back at our problem definition was n. So that's going to be num. And we're going to add to that the solution to the smaller problem. So the way we solve the smaller problem is we invoke our same method, sum integers, and we send in our reduced problem size, which is num minus 1. So again, what we're saying is this is my solving of the small part of the problem now. And then I add on to that my solving of the reduced problem later. And I find that answer to the reduced problem by calling the same method, my recursive method, with the reduced problem size. So if I invoke this method with the value of 5, I get the answer of 15 because 5 plus 4 plus 3 plus 2 plus 1 is 15. So let's trace through what happens here. Okay, so when I invoke this method, well, my first method I invoke is main with the formal parameter args and the local variable. I'm going to ignore the x or the s for now. I didn't create any local variable, so I'm just going to take main and I'm going to push it on the runtime stack. And what main does is it invokes a method called sum integers. And that sum integers has a formal parameter called num, and that formal parameter is sent in the actual value of 5. And that method is pushed onto the stack, and then that method executes. So I go into that method, it says, okay, is num equal to 1? No, it's not equal to 1. So I go into my else, and what I say is, okay, well, what I want to do next is I want to return the value of num plus whatever that is returned from this method. Now, in this method, I could be invoking something else, right? I could be invoking method D or some other method. It works exactly the same. The difference is instead of invoking some other method, I'm actually invoking the same method with just a reduced parameter. Okay, so this is going to say, all right, what I need to return from this method is 5 plus something. And that something is just going to be on pause. This method's going to wait for the value that's returned from the next method. And the next method just happens to be the same one. But because it's a new invocation of that method, I set up a whole new activation record. Okay, so I set up a whole new activation record. I get a new formal parameter called num, and this time num is sent in with 5 minus 1, so num is sent in with the actual value of 4. And this method is now put on the stack. And so we go in and execute this method. We say, is num equal to 1? No, it's not. So what I want to do is I want to return 4 plus whatever answer is given by this method invocation. And this method that I'm going to invoke, again, it could be any method. And if it was, I would have to execute that method until I got some integer returned to me. Just so happens that it's not any method, it's the same method. But that's really the only difference. The way we treat it is exactly the same. So I'm treating it the same. I'm creating a new activation record, and this time num is 3. And I put that activation record on the stack. And then I say, okay, is 3 equal to 1? Nope. So I'm going to go into my else and return 3 plus, well, I need to wait because I don't know the answer to the next method call yet. Just going to shrink these for a minute. So that next method call, again, is the method sum integers with the formal parameter num, which now has the value of 2. So I put that on the runtime stack. Okay. And that says, is 2 equal to 1? No, it's not. So I'm going to go into my else and return 2 plus, I got to wait for my answer. And that answer is going to be whatever is returned from the next method which is invoked, which again is the method sum integers, with now the formal parameter num equal to 1. So I put that on the top of my stack. And once I'm executing this, I say, oh, is num equal to 1? It is. So this whole method's now done. I pop it off my stack, but this method returns an answer. That answer is 1. And so now this is the method that is currently being executed, this version of sum integers. But now this method is done, and now I have a return value. That value is 3. So I pop this off the stack. It's done. And here, I don't have to wait anymore. I have an answer. And that answer is 6. That means that's the end of this method. So this method gets popped off the stack. It's done. And now this method was waiting, but I have an answer. It's 6. Now this method is done, so I pop it off the stack, and I have a number to return. It's 10. And now this method is done, so I pop it off the stack, and I have a number to return. That's 15. And inside my main method, which now continues executing, I have just a print line statement that prints out the whole result of calling this chain, which is 15. Main is then done. It gets popped off the stack, and my whole program is done. So this idea that when we invoke a method, any method, this information about the method, the formal parameters and the value that was sent in as an actual value, and any local variables is contained in an activation record, and that activation record is put onto the stack. All of that information is local and only visible inside that activation record. So if that method calls itself recursively, that second method call gets a whole new activation record and all new copies of these parameters and these local variables. So even though the names of those things are the same, they're totally distinct from each other. This activation record is totally distinct from this activation record. And understanding that and being able to trace that is the key to being able to write and trace through recursive methods. So we're going to go through many more examples of writing these recursive methods, but make sure you understand this very first trace of how it works, because that's going to be key to understanding the more complex methods that we're going to take a look at next.